All right, today we're going to go through some of the orbital mechanics and some of the terms that we use for space flight. I'm going to show you a couple things. First, we're going to talk about the Kármán line, which is the internationally recognized definition of where space begins, and that is 100 kilometers up. That's actually still within inside the atmosphere, right? Now, if you look into here, down here you have like troposphere, stratosphere, mesosphere. So the Kármán line is right above the mesosphere right here at 100 kilometers up, or 100,000 meters. Take your pick. Now, above that, this is also where the auroras apparently begin, so I did not know that, at least according to Wikipedia. Uh, uh, the space station and a lot of the low Earth orbit satellites and stuff, they'll be between the Kármán line and all the way up to the limit of the exosphere. Like I'm pretty sure SpaceX's Starlink system functions between 400 and 500 kilometers. Above that, then you have the exosphere all the way up to about approximately 10,000 kilometers. And at that point, you're definitely in space, like absolutely definitely. There's also very little in the way of atmosphere, but there is some atmosphere. Uh, this is actually one of the things that people don't realize, that even though you don't seem to feel it up in space, it's still there. It's just very gradual. So even around the Kármán line, your orbit is going to decay when you're actually there, which is one of the reasons why a lot of the newer satellites, the newer communication satellites, they've been using that to essentially deorbit themselves. Because I think they'll be able to be deorbited in like 5 years if you lose contact with one of them. So at least that's what I've read so far. I haven't. I need to come up with a source for that again, because I read that a couple years ago. Now, going with orbital mechanics, here's the velocity and then the gravitic acceleration. Earth's gravity specifically is 9.81 meters per second. That means when you're 100,000 meters up, then you're going to be dropping. If you're not if you don't have any velocity, you're going to start having inward velocity or inward acceleration, gravitic acceleration, I guess, uh, of 9.81 meters per second as you drop. And every second that you drop and you continue accelerating down toward the surface and then splat. Uh, we'll talk about that a little bit later. Uh, but this also has some things to do with it'll get very interesting a little later. In For the gravity of the Earth, there's also something very interesting that people were able to find, and that's actually that the Earth's gravity is not uniform. Uh, every section of around the Earth actually has a little bit of a variation in the amount of gravity that is uh, placed on a particular on an object in orbit. And I'm actually going to show you a heat map that is just on Wikipedia. You can look it up yourself, etc. So over here, you see there's uh, Indonesia has a bunch of red spots, and then Japan has a bunch of red spots, all the way up to Russia right here. And then all along the Pacific Rim, basically, you have these red spots, which are an increase in gravity. Uh, this probably means, because that's actually that entire thing is the borders of a continental shelves, so that everything around there is volcanic. which probably means that it's made of a different composition. So you'll have things like you'll have things that are very different from each other with in regards to gravity, like uh, just because the composition of those things, like water, is going to be collect a different gravity than the same amount of uh, the same volume of steel or something, or rock, or just mineral deposits, that sort of thing. And that's actually interesting because it does come up with a lot of possibilities. There might be some way in the future of being able to identify materials just using the gravity and the volume of a rock. It's very possible. Uh, and then down up here, you have the part of the Mid-Atlantic Shelf, uh, and that is also very, very volcanic. Again, it's a there are plate tectonics at work. The one other thing that to note is if you see here, it's in the Himalayas. That part's really easy to identify because it's just a mountain of rock on itself. And because of that mountain of rock, then you have a lot more gravity. But here's a couple of really interesting things. You have Hudson Bay up here in North America. You have the Eastern Caribbean, and then you have the Central Indian Ocean. They're all uh, low in gravity compared to the rest of the areas. It's very interesting to see. Now, when that's ignore that. I'll do that for another video. Uh, so when you actually get into orbit, you'll have to deal with all of that sort of thing, the gravity, etc. Uh, Now, when you do get into orbit, there are a couple things. You have to accelerate uh, fast enough to counteract the acceleration of the gravity. And it's going to be, and that and the friction from the atmosphere and the what do you call it, the variation of gravity, that's going to all affect the interaction of your ship to or a satellite or whatever you launch into orbit uh, before practically everything else. That's one of the reasons why, even though you might feel weightless, it's actually microgravity. Uh, it's not actual zero G. You have it's basically microgravity to the point where you may as not you may as well not have any. So with that, I will see you later.